Imagine you're at a picnic and you're holding a cup of water. If you look into that cup of water and you see a tiny fly, you can easily reach in and pick it out. Now, if you put the same tiny fly in an Olympic-sized swimming pool and try to get it out, it's much more difficult. Locating that tiny fly in a giant swimming pool is how you can imagine locating trace contaminants that may harm your health from your drinking water. That's the focus of my research. I look at how we can better find trace concentrations of a group of harmful contaminants called N-nitrosamines in our drinking water. Now, why do we care about trace concentrations? Some water contaminants can be very harmful to health, even at very low levels. For instance, the United States Environmental Protection Agency, or EPA, suggests a human health protective level at 0.1 part per trillion for NDMA, one of the nitrosamines that I study. That's even less than the tiny fly in the Olympic-sized pool. NDMA is a probable human carcinogen, and it has the potential to exist at these very low levels in some drinking waters. So for that reason, we can't see it, but we have to care about it. Now, even with our very sensitive modern analytical tools, it can be very difficult to see anything at trace levels. This can create a problem because our ability to see water contaminants informs our ability to regulate them and protect our drinking water. My work focuses on how to see those very low concentrations for nitrosamines and to go beyond what the US EPA suggests. To do this, I look at how to take NDMA and other nitrosamines out of water and concentrate them, much like frozen orange juice concentrate, before you add water. This is so we can see them better. I am doing a comparison of extraction and concentration methods for NDMA and other nitrosamines from drinking water in order to evaluate if they're present and at what levels. I'm also looking at how NDMA and other nitrosamines act in water, on the materials designed to trap them, much like a fly in sticky fly paper, and on the liquids designed to rinse them off of that sticky material. We can currently see down to 1 part per trillion for NDMA, and there's more work to be done to meet this US EPA suggested limit. These methods enable us to monitor NDMA and other nitrosamines in the drinking water of communities that may be exposed. By creating optimal trace level methods, we can also open the door to analyze other uncharacterized nitrosamines that we reasonably expect to occur in drinking water contaminated with NDMA. So far, these contaminants have not been routinely monitored nor regulated. With the ability to see trace level contaminants, we can better evaluate drinking water like what you and I drink from our kitchen taps in order to better understand exposure risk and work to keep our drinking water safe.